My name is Raymond Cheng, and I'm here at SOCC 2016 to tell you about Radiatus, a shared nothing server-side web architecture that we've been working on at the University of Washington. Now, we were motivated by website compromises. Websites are routinely broken into, resulting in service disruptions, defacement, surveillance, and the one we're all probably too familiar with, massive data breaches. Now, the focus of this talk is going to be remote exploits because they're the most dangerous. Anybody from anywhere on the internet can mount these attacks due to the public-facing nature of websites. And in fact, all the stories above were the result of a remote exploit on the website software. Now, to understand why this happens, here's an architecture diagram of nearly every web service, regardless of which cloud provider or web framework you use. We highlight the clients in orange, which submit requests to the web service, and they can be serviced by any web server. Now, these web servers interpret the HTTP request, potentially log a user in if we're doing authentication, retrieves some amount of content from the databases, assembles a page, and then returns that back to the client. And so what that means is the developer is responsible for properly handling the requests, to administer access control, to prevent information leakage, and any error or vulnerability in server-side logic can potentially lead to access of global data. So I highlight in blue here the trusted computing base. And you'll notice that what this means is that the attack surface is large and remote code execution can be particularly bad. To walk you through a concrete example, here is a bug that was exploited against GitHub in 2012. Now, this is the server-side code that runs when a user issues a post request to this particular URL, and it happens to be the code for updating the SSH key. And you might notice that something is missing here, which is that when we find the key and we try to update the key to the one that the user specifies, it misses any form of security check. So in this case, the most important one that we're missing is potentially an if statement that describes whether or not the user that's currently logged in with this particular session cookie has the authorization to be updating this key in the first place. So what the attacker can then do is, because the attacker specifies both parameters, the user ID and the public key, the attacker was able to upload an arbitrary SSH key to the Ruby on Rails project. Now, multiply this problem by hundreds, dozens. HTTP interfaces are extremely complex because they intermingle authentication, user actions, and content fetching. Here is a small sample of the GitHub Developer API. And commonly, there's both a developer API as well as user-facing HTTP handlers. And a mistake in any one of these could lead to a wider compromise. So specifically, the threat model that we're looking at are external attacks. So a remote attacker can craft arbitrary network requests and submit them to the web service. So this will include anything like code injection, SQL injection, path traversal, buffer overflows, but we're not going to look at insider attacks or attacks that convince the client to do something that the client shouldn't. So for example, these would include things like cross-site scripting or cross-site request forgery. So in the Radiatus work, we wanted to ask the question, suppose we assigned a sandboxed process on the server for every user, and we call this the user container. And so by a shared nothing architecture, what I mean is that any server-side code running on behalf of a user on the server will only be executed inside this isolated sandbox with only access to that user's data. And our goal here is to limit the impact of vulnerabilities. We can't prevent all 0 days, but assuming that an attacker has the ability to exploit a flaw in the application logic, well then that attacker should only have access to the container for the users for which the attacker already has credentials. So as a consequence of this architecture, we now need to solve a set of other challenges to make this architecture work in practice. For example, how do we restructure an application to support the high sharing patterns that we see in web applications today in a way that's compatible with scale? And in this work, we'll analyze the cost of this architecture. So just for reference, here's a quick flashback to the traditional architecture where nearly everything is part of the trusted computing base and everything is shared through a shared database. In Radiatus, users are isolated into sandboxes, and all developer code that is written runs inside these white sandboxes. So in this case, when a user authenticates, instead of being arbitrarily load balanced across a set of horizontally scaled web servers, we replace the load balancer with this user router, which authenticates the user and then routes user requests only to the user container for which it has the authority. And once these requests are forwarded to the user container, it can trigger code inside its own user container, and it's going to be storing data into its own partition. Now, we want to be able to use existing scalable databases, so we write a storage guard which will essentially expose logical partitions to each one of the user containers. So what that means is an attacker, if they were able to find a zero-day vulnerability inside the developer's code, well, that attacker's packets are only ever going to be routed to and handled by the user container for which they have credentials. We also minimize the trusted computing base to the user authenticator, the user router, the storage guard in front of the database, and the container runtime mechanism. Any code that the developer writes is going to be run inside that sandbox. And in fact, the trusted computing base is going to be shared across all Radiatus applications. So the question is, how do we make functional applications under this architecture? Imagine a service like GitHub where a lot of data is shared between users. We want to introduce a cheap message passing mechanism based on distributed capabilities. So let's walk through a concrete example of a Radiatus application. And we wrote a social network on top of this web framework. The first thing to note is that we have passive containers. Each one of these user containers runs identical copies of developer code. So for the most part, these user containers only need to be online when a user is currently logged in. And in fact, because they run identical copies of code, they can be opportunistically spawned and dynamically assigned to users as they log in. So Alice will first authenticate with the user router, and the first thing to note here is that we have limited interfaces. Before Alice even has access to any other interface, it must first authenticate with the user router and get a valid session cookie. Only after that does it have access to the front-end interface of its own user container, where the requests are again routed based on this cookie. So Alice, in this case, sharing a photo, can upload that photo to her own user container. Once inside the user container, then the developer can do additional things across the cross-container interface. Now, this is a third interface only accessible to user containers, and it exposes an RPC-like interface to send messages in between user containers. We require that the developer declare the types of messages that it plans on sending, which is enforced at runtime. So now Alice can save the message to its own logical partition, send that image over to Bob's container, and correspondingly Bob can do log in, download the image, save the image to his logical partition as well. So the end-to-end picture looks like this. Now, this does necessarily mean that there's a little bit of extra programming overhead as a consequence of the model. We also have this new attack surface that didn't exist before, the cross-container interface. So we'd have to design that message interface defensively between user containers. But we do believe this to be a less vulnerable architecture compared to monolithic applications because we limit the interfaces in a defense in depth strategy. Each of these interfaces are thin, and we'll refer to the paper for additional techniques used when a user attacks their own container. But the goal here is to make web applications more secure, not necessarily perfectly secure. Now, actually sending copies of data like images between user containers would be very expensive. So what we want to do is actually use a shared database, but in essence, send pointers to that database and provide a mechanism for access control that's compatible with the shared nothing architecture that we have. So let's say, for example, Alice wants to store some data at key K. Well, the first thing that happens in this distributed capability system is that Alice's runtime will generate a random nonce that's then hashed along with the data, and that hash now forms the capability. so that when Alice wants to actually store this data on the database is, or the storage guard is going to store two tables on the database. One that maps the owner to the capability, and the second that maps the capability to the data itself. Now, Alice can send that capability, which is small, to Bob's user container, and now Bob can directly use that capability to any of the storage guards to retrieve that data. So that capability now provides proof of access. Because we expect the database to be scalable and there to be multiple storage guards, well, this capability can be independently verified by any one of the storage guards, and that allows the database and application to scale independently. We also get the ability to deduplicate data by content hash, and transferring capabilities is cheap, regardless of the content size or the number of users with access. We'll also defer to the paper to learn more about deletion and revocation. We implemented Radiatus in about 8,674 lines of code on top of the Node.js runtime. We use Linux containers for isolation. We've written a storage guard for MongoDB, and we wrote two message routers, a custom one based on WebSockets and one backed by the AWS Simple Queuing service. So as part of our evaluation, we wanted to ask three high-level questions. How many severe web-related vulnerabilities would this architecture address? What is the additional overhead imposed by a single server, now that each server may have to run many separate processes, one for each user? And how far can we push the scale of our application? To understand security, we looked at the 2014 National Vulnerability Database, which tracks software vulnerabilities. And we looked at all 40 of the server-side web software that was assigned the highest severity score. This is a score assigned by the database for remotely exploitable vulnerabilities with high impact. And we manually translated each of these 40 vulnerabilities to a Radiatus architecture. And we found that for 32 of them, we limited the impact to a single container, which is what we wanted. For 3, we prevented entirely. And for 4 of them, we relied on delegated authentication. These are vulnerabilities where the application was trying to write its own authentication and access control mechanisms in a way that was buggy. And in Radiatus, we rely on the fact that all Radiatus applications have to share the same authentication software. And for one of them, it was unclear what the impact was due to the vagueness of the description. Now, this does not account for potential vulnerabilities in the cross-container interface, which is a limitation of the security analysis. But we were able to validate that other types of vulnerabilities, purely on the front-end interface, were addressed by our system. Now, to analyze the single server throughput, we simulated 100 users issuing parallel requests to a simple counter web app. This was a web app that was just showing the number of requests that have been seen to prevent caching. And what's interesting here is specifically the 2 bars for Radiatus and Node.js. Since Radiatus is written on top of Node.js, we showed that we have a maximum single server overhead of about 60.7%. Now, this is the maximum, so we expect as application complexity grows, which most applications should be much more complex than a single counter application, this relative overhead should be less. We also tried to scale Radiatus across 500 nodes on Amazon EC2, and we scaled the number of clients from 1 to 180,000, where each container performs an operation every 4 to 6 seconds. A read in this case would be a read to a personal storage partition, and a write would be sending a message between containers, which is more expensive. And we were able to get throughputs from between 15 to 20,000 operations per second, which is pretty good. As a point of comparison, Wikipedia sees about 414 million readers per month and about 2,000 HTTP requests per second. Now, in terms of cost, the main cost here is the memory, as you'd expect. It costs about 30.5 megabytes per process for the applications that we wrote, and this is predominantly used by spawning an independent Node.js process for each user. Now, assuming 2015 DRAM prices and an average server lifetime of about 3 years, we estimate that it will probably cost about 0.8 cents per user per year. For Facebook, which you can think of as the worst case, they see about 968 million daily active users, and using Little's law and some public numbers, we estimate there's about 26 million concurrent users at any given time, which comes out to be about $200,000 per year for Facebook. Now, comparing the 0.8 cents per user to the $10 to $12 per user that Facebook sees, well, this is a pretty minimal cost for the security that you get. I would anticipate that web applications with the most critical data, like billing systems, etc., may have a different calculation for the cost-benefit analysis, but there is a cost predominantly in memory. There is a lot of research in securing web applications, and I'll briefly just note that most of these techniques are compatible and represent a defense in-depth solution to security. So in Radiatus, we propose an alternative architecture for web application that strongly isolates users in deprivileged sandboxes. We demonstrate that it prevents the most severe web-related vulnerabilities with modest overhead in a way that's compatible with scaling. Due to the prevalence of security attacks on websites today, I think it's time to rethink how we code websites. Thank you.